The primordial Earth that existed over 4.5 billion years ago bore no resemblance to the blue marble we know today. Instead, our planet was a hellish realm of molten rock, perpetual volcanic eruptions, and an atmosphere so toxic and hot that it would have been instantly lethal to any form of life as we understand it. This was the Hadean Aeon, named after Hades, the ancient Greek underworld, and it represents the most extreme and violent period in Earth's geological history. During this epoch, which lasted from Earth's formation approximately 4.4 billion years ago until about 4 billion years ago, our planet was essentially a massive ball of lava, constantly reshaped by cosmic bombardment and internal heat. The surface temperature reached levels that would make Venus seem temperate by comparison, with estimates suggesting temperatures of 1200 to 1600 degrees Celsius across much of the planet's surface. Oceans of magma stretched across continents that didn't yet exist, while the sky glowed with the perpetual fire of volcanic activity. The atmosphere was composed primarily of hydrogen, helium, methane, ammonia, and water vapor, creating a greenhouse effect so intense that it maintained these scorching temperatures even during the planet's early cooling phases. This was truly a world where fire reigned supreme, where the very ground beneath what would one day become mountains and valleys remained in a constant state of molten flux, and where the concept of solid land was virtually non-existent. The formation of this lava world began with the accretion of cosmic debris in the early solar system, a process that generated enormous amounts of heat through gravitational compression and the constant bombardment of asteroids, comets, and planetesimals. As these cosmic bodies crashed into the growing Earth, they released kinetic energy equivalent to nuclear explosions, heating the planet's surface to temperatures that kept rock in a liquid state. The early Earth was essentially a magma ocean, with depths that may have extended hundreds of kilometers below what would eventually become the surface. This global ocean of molten rock was not static. It churned and convected like a massive cauldron, driven by the tremendous heat generated from radioactive decay within the planet's core and the continued bombardment from space. The differentiation of Earth's layers, the formation of the core, mantle, and early crust, occurred within this hellish environment as denser materials sank toward the center while lighter elements rose toward the surface. Iron and nickel migrated downward to form the core, while silicate minerals remained in the upper layers, creating the basic structure that would eventually allow for the formation of a solid crust. However, this process took hundreds of millions of years, and throughout this period the surface remained a turbulent sea of lava, punctuated by volcanic islands that would form and disappear in geological instants as the magma ocean continued its relentless circulation. The late heavy bombardment, which occurred approximately 4.1 to 3.8 billion years ago, represents one of the most catastrophic periods in Earth's fiery history. During this time, the inner solar system was subjected to an intense barrage of asteroids and comets, possibly triggered by gravitational perturbations caused by the migration of the giant outer planets. For Earth, this meant that just as the planet was beginning to cool and develop its first stable crust, it was repeatedly pummeled by impacts that would have remelted vast regions of the surface. Some of these impacts were so massive that they would have vaporized entire proto-oceans, sending superheated steam into the atmosphere and creating temporary increases in surface temperature that could have maintained the molten state across entire continents. This process, known as the steam atmosphere phase, meant that Earth was essentially a giant pressure cooker with temperatures and pressures that would have been instantly lethal to any conceivable form of life. The first signs of cooling came when the heat production from radioactive decay began to decrease and the rate of asteroid bombardment slowed, allowing the upper atmosphere to begin radiating heat into space more effectively than it was being generated from below. The chemistry of the early Earth's lava oceans was fundamentally different from the magma we observe in modern volcanic eruptions, reflecting the unique conditions and compositions that existed during the planet's formation. These primordial magmas were likely much richer in iron and magnesium than contemporary lavas, creating what geologists term ultramafic compositions that would have had different melting points and flow characteristics than the basaltic and andesitic lavas common in more recent geological periods. The high iron content would have given these ancient lava flows a distinctly different appearance, possibly appearing more metallic and reflecting light differently than modern volcanic rocks. The presence of dissolved water and other volatile compounds in these early magmas would have also affected their behavior, potentially making them more explosive when they finally began to cool and solidify. As these iron-rich magmas crystallized, they would have formed olivine and pyroxene minerals that are still found in some of the Earth's oldest rock formations, providing us with clues about the composition and behavior of these ancient molten seas. The differentiation process that occurred within these magma oceans was crucial for establishing the chemical gradients that would eventually lead to the formation of Earth's layered structure, but it also meant that the early crust, when it finally began to form, would have been compositionally distinct from the continental and oceanic crusts that we see today. Understanding the chemistry of these early lavas is essential for reconstructing not only the conditions that existed during Earth's formation, but also the processes that led to the development of the more stable, differentiated planet that would eventually support life. The transition from a completely molten surface to the first solid crust represents one of the most significant milestones in Earth's early history, marking the beginning of the end of the true lava world phase. This process, known as crustal formation or primary differentiation, occurred gradually as the rate of heat production finally began to exceed the rate of heat loss to space. The first solid rocks to form would have been thin, unstable films on the surface of the magma ocean, constantly being broken apart and remelted by convection currents and continued volcanic activity. These early crustal fragments were likely composed of anorthite and other plagioclase feldspars, minerals that form when magma cools slowly and allows large crystals to develop. However, the crust that formed during this period was nothing like the stable continental and oceanic plates we know today. Instead, it was a constantly changing mosaic of solidified lava flows, volcanic islands, and temporary solid patches that could be destroyed and reformed within relatively short geological time spans. The formation of stable crust was hindered not only by the continued volcanic activity, but also by the ongoing bombardment from space, which could shatter newly formed rock and return large areas to a molten state with each major impact. The early crust was also much thinner than modern crustal formations, perhaps only a few kilometers thick in most places, making it extremely vulnerable to destruction by volcanic activity from below. Despite these challenges, the formation of even temporary solid surfaces represented a crucial step in Earth's evolution, as it began the process that would eventually lead to the development of stable land masses and, much later, the conditions necessary for the emergence of life. The atmospheric conditions during Earth's lava world phase were as extreme and hostile as the surface conditions, characterized by crushing pressures, toxic gases, and temperatures that would have made the planet uninhabitable for any known form of life. The early atmosphere was likely composed primarily of hydrogen and helium captured from the solar nebula during Earth's formation. But this primary atmosphere was probably lost relatively quickly due to the intense solar radiation and high temperatures that characterized the early solar system. The secondary atmosphere that developed was created largely through volcanic outgassing, as the constant eruptions released enormous quantities of water vapor, carbon dioxide, sulfur dioxide, nitrogen, and various other gases from Earth's interior. This volcanic atmosphere was incredibly dense, with pressures that may have exceeded 100 times the current atmospheric pressure, creating conditions similar to those found on Venus today. The high concentration of greenhouse gases, particularly water vapor and carbon dioxide, created a runaway greenhouse effect that trapped heat and maintained surface temperatures well above 1,000 degrees Celsius for hundreds of millions of years. The atmosphere during this period would have been completely opaque, filled with clouds of steam and volcanic ash that blocked all sunlight from reaching the surface. Lightning was probably constant, generated by the electrical activity within the dense clouds of steam and volcanic particles, creating a sky that flickered with perpetual electrical storms. The chemical composition of this early atmosphere was highly reducing, meaning that it contained very little free oxygen and was instead dominated by gases that would readily react with oxygen if it were present. The role of impact events in shaping and reshaping Earth's lava world cannot be overstated, as these cosmic collisions provided both the energy to maintain molten conditions and the materials that would eventually contribute to the planet's bulk composition. The early solar system was a chaotic environment filled with debris left over from the formation of the planets, and Earth's position in the inner solar system made it a natural target for countless asteroids, comets, and planetesimals. Each impact released enormous amounts of kinetic energy, which was converted to heat upon collision, often generating temperatures sufficient to melt rock for hundreds of kilometers around the impact site. The largest impacts created temporary magma seas that could persist for thousands of years, while smaller impacts contributed to the general heating of the surface and prevented the formation of stable crust. Some impacts were so massive that they may have temporarily stripped away portions of Earth's atmosphere, only to have it reformed through continued volcanic outgassing. The bombardment was not uniform over time. Periods of intense bombardment alternated with relatively quieter intervals, creating cycles of melting and cooling that influenced the planet's thermal evolution. The composition of the impacting bodies also varied, with some contributing water and organic compounds while others brought primarily rocky material, gradually building up Earth's mass and influencing its chemical evolution. The impact history of the early Earth is recorded in the heavily cratered surfaces of the Moon and other bodies in the solar system, providing us with a window into understanding the intensity and frequency of these early collisions. Without this cosmic bombardment, Earth might have cooled much more rapidly, but the continued influx of impact energy ensured that the planet remained in a largely molten state for the first several hundred million years of its existence. The gradual cooling of Earth from its initial lava world state was a complex process influenced by multiple factors, including the decline in radioactive heating, the decrease in impact frequency, and the planet's growing ability to radiate heat into space. The cooling process was not linear or uniform. Instead, it occurred in fits and starts, with periods of gradual temperature decline interrupted by major impact events that could temporarily reheat large portions of the surface. The first signs of cooling became apparent when the upper atmosphere began to thin enough to allow heat to escape more efficiently, reducing the effectiveness of the greenhouse effect that had maintained the extreme surface temperatures. As the atmosphere gradually became less dense and less opaque, the planet's albedo, its ability to reflect sunlight, began to change, allowing for more efficient heat loss through radiation. The cooling process was also influenced by the gradual decline in volcanic activity as the heat flow from Earth's interior decreased with time. However, even as the average surface temperature began to drop, large regions of the planet remained molten for millions of years after the cooling process began, creating a patchwork landscape of solidified crust and active lava flows. The cooling was not uniform across the planet's surface. Polar regions may have begun to solidify earlier than equatorial areas, creating temperature gradients that would influence atmospheric circulation patterns and weather systems. The transition from a completely molten surface to a partially solid one created new geological processes, including the first primitive forms of erosion and sedimentation. As temporary streams of liquid rock began to carve channels and deposit materials in patterns that would foreshadow the more complex geological processes that would dominate later periods in Earth's history. Continental formation during and immediately after the lava world phase represents one of the most significant and poorly understood aspects of early Earth history, as the processes that led to the development of stable landmasses operated under conditions completely unlike anything we observe today. The first protocontinents were likely formed through the partial differentiation of the magma ocean as lighter, silicate-rich materials rose to the surface and began to accumulate in relatively stable masses. These early continental nuclei were small, unstable, and constantly being modified by volcanic activity. But they represented the first step toward the development of the large, stable landmasses that would characterize later geological periods. The formation of these early continents was complicated by the high heat flow from Earth's interior, which made it difficult for thick, stable crust to develop and persist over long periods. Instead, the early continental masses were likely thin, hot, and highly mobile, constantly being recycled back into the mantle through processes that were much more rapid and efficient than modern plate tectonics. The composition of these early continental masses was also different from modern continents, likely being richer in magnesium and iron and poorer in the lighter elements like silicon and aluminum that characterize contemporary continental crust. The growth of these proto-continents occurred through a combination of volcanic addition, where new material was added from below through continued eruptions, and accretion, where smaller crustal fragments were welded together through tectonic processes. The development of stable continental masses was crucial for Earth's long-term evolution, as these land masses would eventually provide the stable platforms necessary for the development of complex geological processes and, much later, the emergence of terrestrial life. However, during the lava world phase, continental formation was a constant battle between creation and destruction, with new crustal material being formed through volcanic processes, even as existing formations were being destroyed by continued heating and bombardment. The chemical evolution of Earth's early oceans of magma played a crucial role in determining the eventual composition of the planet's crust, mantle, and core, setting the stage for all subsequent geological and biological evolution. These vast bodies of molten rock were not simply uniform pools of liquid. Instead, they were complex chemical systems where different elements and compounds, separated according to their densities, melting points, and chemical affinity. The process of fractional crystallization within these magma oceans led to the development of chemically distinct layers, with denser, iron-rich materials sinking toward the bottom while lighter, silicate-rich materials rose toward the surface. This differentiation process was driven not only by gravity, but also by the complex thermodynamics of multi-component silicate melts, which behave differently than simple single-component liquids. The magma oceans also served as vast chemical reactors where elements that would later become essential for life, such as carbon, nitrogen, and sulfur, were processed and distributed throughout Earth's interior. The solubility of different gases in these molten systems determined which compounds would be retained within the planet and which would be released into the atmosphere through volcanic outgassing. Water played a particularly important role in these processes, as its presence in magma significantly affects melting temperatures, crystallization sequences, and the behavior of other dissolved components. The chemical gradients established during this early differentiation period would have long-lasting effects on Earth's geological evolution, influencing everything from the composition of volcanic rocks to the development of ore deposits and the eventual formation of soil systems that would support terrestrial life. Understanding the chemistry of these early magma oceans is essential for reconstructing not only the conditions that existed during Earth's formation, but also the processes that led to the development of the chemically diverse planet that we inhabit today. The eventual formation of the first stable water bodies on Earth marked the beginning of the end of the lava world, epoch, representing one of the most significant transitions in planetary history. This process began when surface temperatures finally dropped below the critical point of water, allowing steam in the atmosphere to begin condensing into liquid droplets. However, the transition was not immediate or complete. For millions of years, Earth experienced cycles of evaporation and condensation as temporary pools of water would form during cooler periods only to be vaporized again when volcanic activity increased or when large impacts occurred. The first stable bodies of liquid water were likely small, temporary lakes that formed in topographic depressions created by volcanic activity or impact craters. But these early water bodies were extremely hot, near the boiling point, and highly acidic due to the dissolution of volcanic gases. These primitive oceans and lakes were also highly mineralized, containing dissolved metals and compounds leached from the surrounding volcanic rocks. The chemistry of these early water bodies was unlike anything that exists on Earth today, with pH levels that would have been extremely acidic and concentrations of dissolved minerals that would have made the water toxic to any conceivable form of life. Despite these harsh conditions, the presence of stable liquid water represented a fundamental change in Earth's surface processes, as it enabled new types of chemical reactions and physical processes that would eventually lead to more moderate conditions. So, the formation of water bodies also began to moderate the planet's temperature through the high heat capacity of liquid water, which could absorb and store large amounts of thermal energy, helping to buffer against extreme temperature fluctuations. The interaction between hot water and volcanic rocks also initiated the first large-scale weathering processes, beginning the slow transformation of the planet's surface chemistry that would eventually create the more hospitable conditions necessary for the emergence of life. Life's eventual emergence from this hellish lava world represents one of the most remarkable transitions in the history of our planet, demonstrating the incredible adaptability and persistence of biological systems even under the most extreme conditions imaginable. While life as we know it could not have survived during the peak of the lava world phase, the gradual cooling and stabilization of Earth's surface created increasingly hospitable niches where the first primitive organisms could take hold. The transition from a sterile, molten planet to one capable of supporting life occurred over hundreds of millions of years and involved countless intermediate steps, each representing a small improvement in habitability. The first life forms were likely extremophiles, organisms adapted to conditions of high temperature, acidity, and radiation that could survive in the marginal environments that existed at the boundary between the dying lava world and the emerging biosphere. These early organisms may have originated in hydrothermal environments where hot water interacted with mineral-rich volcanic rocks, creating chemical gradients and energy sources that could support primitive metabolic processes. The development of life during this transition period would have been precarious, with populations constantly threatened by volcanic eruptions, impact events, and dramatic changes in environmental conditions. However, the very instability of the early Earth may have accelerated evolutionary processes by creating strong selective pressures that favored organisms capable of rapid adaptation and survival under changing conditions. The chemical diversity created by ongoing volcanic activity also provided a rich array of compounds and energy sources that early life forms could exploit, setting the stage for the development of the complex biochemical pathways that characterize modern living systems. The transformation of Earth from a lava world to a living world was not just a physical and chemical process, but also a biological one. as early life forms began to influence their environment through processes like photosynthesis and mineral precipitation, gradually creating the conditions that would support more complex forms of life. The geological legacy of Earth's lava world phase can still be observed today in some of the oldest rock formations on the planet, providing us with direct evidence of the extreme conditions that characterized our planet's early history. These ancient rocks, found in places like the Canadian Shield, Western Australia, and Greenland, contain mineral assemblages and chemical signatures that could only have formed under the high temperature, high pressure conditions that existed during the Hadean and early Archean eons. Zircon crystals, some of the oldest materials found on Earth, preserve information about magma temperatures and compositions from over 4 billion years ago, offering glimpses into the chemistry and behavior of the ancient magma oceans. These geological records suggest that Earth's transition from a lava world to a more habitable planet was gradual and complex, involving multiple stages of cooling, solidification, and renewed heating due to impact events and volcanic activity. The oldest sedimentary rocks provide evidence that liquid water was present on Earth's surface by at least 3.8 billion years ago, indicating that the transition away from completely molten conditions was largely complete by this time. However, the presence of banded iron formations and other unusual rock types in these early geological records suggests that Earth's surface conditions remained extreme by modern standards for hundreds of millions of years after the end of the lava world phase. The study of these ancient rocks has revolutionized our understanding of early Earth conditions and has provided crucial constraints on models of planetary formation and evolution. These geological archives also contain the earliest evidence for life on Earth, suggesting that the transition from a sterile lava world to a living planet occurred relatively rapidly once suitable conditions were established. The preservation of these ancient rocks is itself remarkable given the violent conditions under which they formed, and their survival provides us with an invaluable window into one of the most dramatic periods in Earth's history. Modern volcanic activity provides us with the closest analog we have to understanding what Earth's surface might have been like during the lava world phase, though even the most extreme contemporary eruptions pale in comparison to the global volcanic activity that characterized the early Earth. Large igneous provinces like the Deccan Traps in India and the Columbia River basalts in North America give us some sense of the scale of volcanic activity that was commonplace during Earth's early history, when enormous volumes of lava could be erupted over relatively short geological time periods. However, these modern examples represent isolated events rather than the continuous, planet-wide volcanic activity that characterized the Hadean eon. Contemporary volcanic lakes, such as those found in some active calderas, provide insights into what the ancient magma oceans might have looked like, though again at a much smaller scale and under much cooler conditions. The study of ultramafic lavas in places like Hawaii and Iceland helps us understand the behavior and composition of the iron and magnesium-rich magmas that dominated early Earth's surface. While laboratory experiments on synthetic magma compositions allow scientists to recreate some of the extreme conditions that existed during the lava world phase, modern hydrothermal systems, both terrestrial and submarine, also provide analogs for understanding how chemical processes operated at the interface between hot rock and water during Earth's transition away from completely molten conditions. These contemporary examples help us interpret the geological record of early Earth and provide testable hypotheses about the processes that operated during the planet's most extreme period. However, it's important to recognize that no modern analog can fully capture the intensity, scale, and duration of the processes that shaped Earth during its lava world phase, making this period one of the most challenging to understand in the entire geological record. The comparative study of other planets in our solar system provides additional context for understanding Earth's lava world phase and the conditions that characterized the early terrestrial planets. Venus, with its surface temperature of over 450 degrees Celsius and dense carbon dioxide atmosphere, may represent what Earth was like during parts of the lava world phase, though Venus's current conditions are maintained by a runaway greenhouse effect rather than active volcanism. Mars shows evidence of having experienced extensive volcanic activity in its early history, with massive shield volcanoes and vast flood basalt provinces that suggest the red planet may have gone through its own lava world phase, albeit on a smaller scale than Earth. The moon's heavily cratered surface preserves evidence of the late heavy bombardment that also affected Earth, providing crucial information about the timing and intensity of the impact events that prolonged Earth's molten phase. Jupiter's moon Io, with its continuous volcanic activity driven by tidal heating, offers a modern example of what a volcanic world might look like, though under very different conditions than those that existed on early Earth. The study of exoplanets has also revealed that lava worlds may be common in the universe, particularly among planets that orbit close to their host stars, suggesting that the extreme conditions Earth experienced during its early history may be a normal part of planetary evolution. These comparative studies help us understand that Earth's lava world phase was not unique, but rather represents a natural stage in the evolution of rocky planets. They also help us appreciate the remarkable transformation that our planet has undergone from a hellish world of molten rock to the temperate, life-supporting planet we know today. The fact that Earth successfully made this transition while other planets did not highlights the delicate balance of conditions that were necessary for our planet to become habitable. The technological and scientific methods used to study Earth's lava world phase represent some of the most sophisticated and interdisciplinary approaches in modern science, combining techniques from geology, geochemistry, planetary science, and experimental petrology. High-temperature and high-pressure experiments in specialized laboratory facilities allow scientists to recreate some of the conditions that existed during the magma ocean phase, helping to understand how different materials behave under extreme conditions and how the differentiation of Earth's layers might have occurred. Advanced analytical techniques, such as mass spectrometry and electron microprobe analysis, enable researchers to study the chemical composition of ancient minerals and rocks with unprecedented precision, revealing information about the temperature, pressure, and chemical conditions under which they formed. Numerical modeling and computer simulations help scientists integrate observational data with theoretical understanding to create comprehensive models of how Earth's early evolution might have proceeded. These models can test different scenarios for planetary formation and evolution, helping to constrain the timing and mechanisms of the transition from lava world to habitable planet. Isotopic analysis of ancient rocks provides information about the timing of different geological processes and the evolution of Earth's atmosphere and hydrosphere during the transition away from molten conditions. Remote sensing and space-based observations of other planets and moons help provide comparative context for understanding Earth's early evolution and the processes that operate on planetary scales. The integration of all these different approaches has revolutionized our understanding of Earth's early history and has revealed the remarkable complexity of the processes that shaped our planet during its most extreme period. However, many aspects of the lava world phase remain poorly understood, and continued research using new technologies and approaches will undoubtedly reveal additional insights into this fascinating period of Earth's history. The implications of Earth's lava world phase extend far beyond academic curiosity about our planet's early history, influencing our understanding of planetary formation, the conditions necessary for life, and the potential habitability of exoplanets throughout the universe. The recognition that Earth spent hundreds of millions of years as an essentially sterile, molten world has important implications for understanding the timing and mechanisms of life's emergence, suggesting that the transition to habitability may be a relatively rapid process once appropriate conditions are established. This understanding also influences how we search for life on other planets, as it suggests that even planets that appear extremely hostile today may have the potential to become habitable given sufficient time and the right combination of conditions. The study of Earth's lava world phase has also contributed to our understanding of the factors that determine whether a planet will successfully transition to habitable conditions or remain permanently hostile to life. These insights are particularly relevant as astronomers discover increasing numbers of exoplanets, many of which may currently be in their own lava world phases. The extreme conditions that characterized early Earth also provide natural laboratories for studying the behavior of matter under conditions that are difficult or impossible to recreate in terrestrial laboratories, contributing to our fundamental understanding of physics and chemistry. From a philosophical perspective, the recognition that Earth was once a completely sterile world highlights the remarkable nature of the transformation that led to the emergence of life and the development of the complex biosphere we see today. This perspective can inform discussions about planetary stewardship and the preciousness of the habitable conditions that currently exist on Earth. The study of the lava world phase also demonstrates the power of scientific methods to reconstruct events that occurred billions of years ago, showcasing humanity's ability to understand and interpret the most extreme conditions in our planet's history. Earth's journey from lava world to living world represents one of the most dramatic transformations in the history of our solar system, demonstrating the remarkable capacity of planetary systems to evolve from utterly hostile conditions to environments capable of supporting complex life. This transformation required hundreds of millions of years and involved countless intermediate steps, each representing a small but crucial improvement in habitability. The cooling of the global magma ocean, the formation of the first stable crust, the condensation of the first liquid water, and the establishment of the first stable atmospheric conditions all contributed to creating the foundation upon which life would eventually emerge and flourish. The violence and extremity of the lava world phase make the existence of our current temperate, life-supporting planet seem almost miraculous, highlighting the delicate balance of conditions that were necessary for Earth to become habitable. The study of this remarkable transformation continues to yield new insights into planetary evolution, astrobiology, and the fundamental processes that govern the behavior of rocky planets. As we continue to discover and study exoplanets throughout the universe, the lessons learned from Earth's early history will undoubtedly prove invaluable for understanding the potential for life elsewhere in the cosmos. The lava world phase represents not just a fascinating chapter in Earth's history, but a crucial piece of the larger story of planetary evolution and the emergence of life in the universe. Understanding this period helps us appreciate both the remarkable nature of our current world and the long, complex journey that was necessary to create the conditions that allow us to exist and contemplate our own origins. The legacy of Earth's fiery beginnings continues to influence our planet today, reminding us that the stable, habitable conditions we take for granted are the result of billions of years of planetary evolution and represent a precious and perhaps rare outcome in the cosmic story of planetary formation and development. Retry Claude can make mistakes. Please double-check responses. The birth of Earth was not a quiet or gentle event, but rather a violent, chaotic, and fiery transformation that unfolded over millions of years in the young solar system, where dust, gas, and countless fragments of rock were pulled together under the force of gravity to create the building blocks of planets. And in Earth's case, this process generated such an extraordinary amount of heat from collisions, compression, and radioactive decay that the entire planet became a swirling ocean of molten rock and metal, glowing like a star as it rotated through space. Imagine vast torrents of magma bubbling and surging across the surface with no distinction between land and sea, a place where nothing could exist except fire and liquid stone, where the sky itself was thick with vaporized rock and gases blasted into the air by never-ending impacts, where temperatures soared so high that even solid minerals dissolved into a glowing liquid, and where the relentless rain of planetesimals, fragments left over from the formation of the solar system, slammed into the young Earth, releasing energy comparable to nuclear explosions, each collision shaking the planet to its core and maintaining the inferno. This stage, often described as a magma ocean era, was fundamental in shaping the very structure of our world, because as the molten mass churned and seethed, heavier elements like iron and nickel sank inward to form the core, while lighter silicates floated upward to create the beginnings of a primitive mantle and crust. And even though it was chaotic and destructive, this molten state provided the foundation for everything that would come later, for it was during this time that Earth's layered structure, the metallic core, the rocky mantle, and eventually the crust, was born out of fire, ensuring that the planet would one day develop a magnetic field to protect life, continents to anchor ecosystems, and volcanism to recycle materials. But at this early stage, it was only a hellish sphere of flame and rock where no air was breathable, no ocean could exist without instantly boiling away, and no life could survive in the storm of fire, lightning, and impacts. Yet in this seemingly hostile inferno lay the seeds of habitability, because the same fiery forces that made the world unbearable were also mixing, melting, and redistributing the raw elements that would later combine to form oceans, an atmosphere, and eventually life. So if we imagine standing on the surface of this primordial Earth, though impossible for any human, it would be like standing inside a furnace the size of a planet, surrounded by seas of lava stretching to the horizon, with glowing rivers of molten stone flowing endlessly into vast, churning basins. Above which the sky was not blue, but a suffocating haze of vaporized minerals, sulfurous gases, and incandescent dust, illuminated by the flashes of impacts from falling space rocks, a landscape so alien and extreme that it resembled not the home we know today, but rather the surface of a star crossed with the volcanic chaos of Jupiter's moon, Io, a place where fire was not only a destructive force but also a creative one, shaping the destiny of Earth from its very beginning. The birth of Earth was not a quiet or gentle event, but rather a violent, chaotic, and fiery transformation that unfolded over millions of years in the young solar system, where dust, gas, and countless fragments of rock were pulled together under the force of gravity to create the building blocks of planets. And in Earth's case, this process generated such an extraordinary amount of heat from collisions, compression, and radioactive decay that the entire planet became a swirling ocean of molten rock and metal, glowing like a star as it rotated through space. Imagine vast torrents of magma bubbling and surging across the surface with no distinction between land and sea, a place where nothing could exist except fire and liquid stone, where the sky itself was thick with vaporized rock and gases blasted into the air by never-ending impacts, where temperatures soared so high that even solid minerals dissolved into a glowing liquid, and where the relentless rain of planetesimals, fragments left over from the formation of the solar system, slammed into the young Earth, releasing energy comparable to nuclear explosions, each collision shaking the planet to its core and maintaining the inferno. This stage, often described as a magma ocean era, was fundamental in shaping the very structure of our world, because as the molten mass churned and seethed heavier, elements like iron and nickel sank inward to form the core, while lighter silicates floated upward to create the beginnings of a primitive mantle and crust. And even though it was chaotic and destructive, this molten state provided the foundation for everything that would come later. For it was during this time that Earth's layered structure, the metallic core, the rocky mantle, and eventually the crust, was born out of fire, ensuring that the planet would one day develop a magnetic field to protect life, continents to anchor ecosystems, and volcanism to recycle materials. But at this early stage, it was only a hellish sphere of flame and rock where no air was breathable, no ocean could exist without instantly boiling away, and no life could survive in the storm of fire, lightning, and impacts. Yet in this seemingly hostile inferno lay the seeds of habitability, because the same fiery forces that made the world unbearable were also mixing, melting, and redistributing the raw elements that would later combine to form oceans, an atmosphere, and eventually life. So if we imagine standing on the surface of this primordial Earth, though impossible for any human, it would be like standing inside a furnace the size of a planet, surrounded by seas of lava stretching to the horizon, with glowing rivers of molten stone flowing endlessly into vast, churning basins, above which the sky was not blue but a suffocating haze of vaporized minerals, sulfurous gases, and incandescent dust, illuminated by the flashes of impacts from falling space rocks. A landscape so alien and extreme that it resembled not the home we know today, but rather the surface of a star crossed with the volcanic chaos of Jupiter's moon, Io. A place where fire was not only a destructive force, but also a creative one, shaping the destiny of Earth from its very beginning. In the broader theater of the solar system, the process that forged Earth into a molten world of fire was not an isolated event, but part of a larger cosmic drama in which countless planetesimals, small planetary seeds formed from dust and gas, were constantly colliding, merging, and shattering. And each collision unleashed an extraordinary amount of energy, enough to keep the entire planet in a molten state for millions of years. And when these planetesimals slammed into the growing Earth at speeds of tens of kilometers per second, the kinetic energy transformed instantly into heat, vaporizing rock, creating temporary craters that filled with lava, and throwing up incandescent plumes that rained molten droplets back to the surface like fiery meteors. The scale of destruction was immense, yet this ceaseless bombardment was paradoxically constructive, because without the violent energy of impacts, Earth would not have fully differentiated into its layers, nor would it have received many of the elements essential for life, as some planetesimals carried volatile compounds such as carbon, nitrogen, and possibly even water in their minerals. So while the impacts melted the planet into a seething ocean of magma, they also seeded it with the raw ingredients for the future biosphere, making them both destroyers and benefactors. If we picture this epoch, Riese resembled a glowing ember in space, its surface continually churned by colossal impacts, its skies filled with incandescent debris from shattered bodies, and its crust never allowed to cool long enough to solidify before another collision remelted it. And while for us such conditions seem utterly catastrophic, in the language of planetary formation, this was the necessary process of planetary accretion, a violent sculpting that ensured Earth would become large enough, dense enough, and geologically active enough to sustain oceans, atmospheres, and eventually life. Because without the heat generated by these collisions, the planet might have remained a frozen, barren rock like some asteroids, but instead it was hammered into fire, molded by collisions, and shaped by cosmic violence into the world that would one day become our home. Among the most dramatic events of this fiery youth was the colossal impact believed to have given birth to the moon, a collision so vast that it dwarfs anything humanity can easily imagine, when a Mars-sized body, often called Theia, struck the young Earth with such unimaginable force that entire sections of Earth's mantle were blasted into orbit, creating a glowing ring of molten rock that eventually coalesced into our lunar companion. And this event not only reshaped Earth's surface, but also stabilized its future. Because the newly formed moon would exert gravitational control over Earth's tilt and tides, preventing chaotic swings in climate and helping maintain the long-term stability needed for life to evolve. But in the immediate aftermath, it was pure fire and chaos. With Earth's surface remelted into an even deeper global magma ocean, the atmosphere thick with vaporized rock, and the sky dominated by a fiery glowing proto-moon that loomed far larger than today's moon, shining like a molten lantern in the sky. The energy of this impact was so immense that the entire planet likely glowed for thousands of years as heat radiated into space. And while destructive, this event further enriched Earth by mixing its internal layers, accelerating differentiation, and contributing to the dynamic geological engine that would drive volcanism, plate tectonics, and magnetic shielding. So although it was an unimaginable catastrophe, it was also one of the most pivotal turning points in Earth's fiery creation story, ensuring that from destruction came both a satellite to guide Earth's rhythms and a geophysical structure capable of sustaining a living world. Amid this furnace of impacts and molten landscapes, volcanic outgassing became one of the most important processes shaping the destiny of Earth. Because as the mantle boiled and churned beneath the surface, it released vast quantities of gases through volcanic vents and fissures. And though the atmosphere we breathe today is rich in oxygen, the primordial atmosphere was nothing like it. Instead, it was a suffocating shroud of carbon dioxide, methane, ammonia, nitrogen, sulfur dioxide, and most importantly, steam, all pouring out from Earth's fiery wounds in colossal quantity, creating a sky that was dark, toxic, and heavy with greenhouse gases. Every eruption on this magma-drenched Earth was not just a flow of lava, but also a release of entire oceans worth of vapor. And the cumulative effect of this relentless outgassing was the creation of a dense, choking atmosphere that trapped heat and prevented Earth from cooling quickly, making the world a self-sustaining furnace. Yet paradoxically, this same atmosphere was vital for what was to come, because the steam and vapor it contained would eventually condense into rain when Earth cooled enough, filling the basins with liquid water to form the first oceans, while gases like carbon dioxide would help regulate planetary temperature through greenhouse cycles, creating the delicate balance that made liquid water stable. Oh no. So although in its youth Earth's skies would have appeared orange or even red from the dense haze of volcanic dust, lightning flashing across the horizon and thunder echoing above boiling lava seas, this hellish sky was the ancestor of the breathable air we know today, a toxic womb out of which life would eventually emerge. Thus, volcanic outgassing, born of fire, destruction, and chaos, was in fact the first step toward the nurturing atmosphere that would make Earth unique among planets. Another example of how fire was not only Earth's torment, but also midwife, guiding it from inferno to sanctuary. Within this storm of fire and gas, the atmosphere itself became a theater of chemical chaos. A sky filled with energy, lightning, and reactions that would lay the groundwork for life. Because as steam and carbon dioxide mingled with methane, ammonia, and hydrogen, they created an unstable chemical soup that was constantly being ignited by the crackling bolts of lightning that streaked across the dense clouds, each strike breaking molecules apart and recombining them into new compounds, some of which may have been the precursors to organic molecules like amino acids. And so the fiery sky was not only destructive, but also creative, acting as a vast laboratory powered by fire, electricity, and pressure. Imagine the scene above early Earth. Towering clouds swollen with volcanic gases, their undersides glowing with the reflection of lava oceans below, and within them lightning storms flashing endlessly, creating a rhythm of fire across the heavens. While meteors from the bombardment added bursts of additional energy by vaporizing on entry, each streak across the sky both a destructive flame and a chemical spark for new possibilities. This was a world where fire was not limited to the surface but extended into the very air, with the skies themselves alive with combustion, electrical storms, and chemical reactions. And though no living creature could have survived in such an environment, then the very building blocks of life may have been forming in this fiery crucible, suspended in droplets of rain that evaporated before reaching the molten ground, or deposited in temporary pools that sizzled away within moments. A cycle of endless creation and destruction that repeated for millions of years, until at last conditions stabilized enough for water to remain on the surface. Thus, the fiery skies of early Earth, terrifying and alien though they seem, were in truth the stage upon which the first whispers of biology may have been born. A paradoxical laboratory in which fire, lightning, and gas combined to prepare the way for the miracle of life. As the skies roared with lightning and the surface writhed in oceans of fire, the earliest attempts at solid ground were fleeting and unstable. for whenever thin crusts began to form on the surface of the molten seas, they were almost immediately broken apart by the convective surges of magma rising from the mantle, creating a patchwork of temporary islands that resembled floating rafts on a blazing sea. Glowing cracks splitting open to release fountains of lava that spilled across the crust and swallowed it back into the furnace, and so early Earth could never achieve rest. For the crust was like the scab of a wound constantly torn away, healing only to be broken again by the restless interior heat. In this world, land as we understand it did not truly exist, and yet these short-lived crustal fragments were important because they represented the earliest beginnings of differentiation, with lighter minerals crystallizing and floating while heavier materials sank, a process that gradually allowed more complex rock structures to form. And though the scene was catastrophic and unstable, it was the first step in the journey toward continents, the first outlines of land that would one day rise above oceans to host forests, deserts, mountains, and eventually civilizations. To stand on such proto-crust, had it been possible, would have been to stand on trembling ground above a boiling abyss, where every step could collapse into molten stone, where the air shimmered with heat and the sound of cracking rock and erupting lava never ceased. World where ground itself was a temporary illusion, fragile in the face of fire. Yet these brief appearances of solid rock marked Earth's determination to evolve beyond being a mere sphere of magma, hinting that in time, fire would give way to stability, and chaos would give birth to land. If we attempt to imagine the scale and ferocity of Earth during its fiery youth, perhaps the best modern comparison is Jupiter's moon Io, the most volcanically active body in the solar system, whose surface is constantly reshaped by lava fountains that leap hundreds of kilometers high, sulfurous plumes that stain the skies, and rivers of molten rock carving new landscapes every year. And in many ways, early Earth was like a giant version of Io, only hotter, larger, and even more chaotic. For while Io today is driven by tidal heating from Jupiter's gravity, Earth's fire was born of its own collisions, radioactivity, and formation energy. Yet the results were similar: a world of endless lava lakes, skies filled with volcanic haze, and a surface that never remained the same. Envision Earth as a glowing orb where continents did not yet exist, where instead vast plains of molten basalt stretched in every direction, interrupted only by rivers of fire or the occasional towering volcano pouring fountains of lava skyward, while above clouds of sulfur, and steam turned the sky into a choking veil, illuminated not by sunlight alone, but by the glow of lava reflecting upward, giving the entire horizon a crimson hue. To any observer, though none could exist then, it would have been a terrifying yet magnificent sight, a planet alive with fire, thunder, and motion, closer to a celestial forge than the living sanctuary we know today. And yet it was precisely this resemblance to Io that underscores the universality of volcanic youth in planetary bodies, for where there is heat and molten rock, there is possibility. And though Io today is sterile and lifeless, Earth's fiery twin diverged by cooling just enough capturing its volcanic energy into a long-term cycle that would eventually foster oceans, continents, and life, proving that even the most violent worlds hold within them the seeds of transformation if they can endure the firestorm long enough. As Earth's crust began its uncertain struggle to solidify, the planet birthed colossal volcanoes whose magnitude is beyond modern imagination, mountains of fire that rose not gently but explosively from the seething mantle, pouring out so much molten rock that they dwarfed even the greatest volcanoes we know today, such as Mauna Loa or Olympus Mons on Mars. These proto-volcanoes may not have looked like mountains at all, but rather sprawling fissures and shield-like structures, vomiting rivers of lava that entire hemispheres. There flows uninterrupted for centuries, creating layers upon layers of basalt that served as the foundation for future continental masses. And each eruption was not only a display of geological violence, but also a chemical revolution. For with every outpouring of magma came a vast release of gases into the atmosphere, altering its composition and further thickening the veil of greenhouse gases that would one day allow oceans to remain liquid. To stand near such a volcano, if such a thing were possible, would have been to stand at the edge of the planet's heart, where fountains of lava soared into the sky like glowing rivers of stars, and the ground shook with endless tremors, while the heat was so great it would vaporize any material before it could reach safety. Yet these titans of fire were not simply engines of destruction, but also the great architects of land, for in their ceaseless eruptions they built the first true platforms of stability, offering crutches of 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 crust that resisted immediate destruction, stepping stones on which continents would eventually rise. And so, while we may think of volcanoes as destroyers in Earth's fiery youth, they were also the primal builders of the solid world. The rivers of lava, unleashed by these titanic volcanoes, stretched across unimaginable distances, flowing not for kilometers, but for thousands of kilometers, blanketing the planet in incandescent stone and creating plains of basalt that were larger than some modern continents. Their glowing streams carving pathways into the surface like arteries of fire, and when one eruption subsided, another began elsewhere, so that the planet seemed locked in a cycle of endless resurfacing, never allowing the land to cool into permanence. To imagine this, picture entire oceans replaced by lava, their glowing waves sloshing against each other in fiery tides, while mountains were swallowed by new flows and valleys filled with molten stone, all beneath skies that shimmered with the reflection of a planet covered in flame. These lava flows were so vast and persistent that they shaped the chemical cycles of the atmosphere, releasing carbon dioxide, water vapor, and sulfur in such quantities that the sky itself became a product of volcanism, and the surface cooled only to be swallowed again in fire. Like a phoenix burning itself to ashes only to be reborn in a new form, modern flood basalts such as the Deccan traps in India or the Siberian traps in Russia give us only a faint echo of these primeval events, for those cataclysms, though devastating, covered perhaps a few million square kilometers, while the lava oceans of early Earth were global in scope, entire seas of fire that stretched unbroken for horizons, reshaping the face of the world over and over. And though no life yet existed to witness this fury, these flows were silently preparing the chemistry of the crust and atmosphere for the miracle of biology yet to come. In considering this stage of fiery Earth, the closest analog in our solar system is indeed Io, Jupiter's tortured moon, where today lava fountains reach hundreds of kilometers high, volcanic plumes choke the thin atmosphere, and the surface is painted in sulfurous yellows, reds, and blacks, constantly renewed by fresh eruptions. But Earth's early volcanism far surpassed Io's, for while Io is sustained by tidal forces from Jupiter, Earth's engine was internal, powered by the leftover heat of accretion, the decay of radioactive isotopes, and the energy of catastrophic impacts. And the result was a world that resembled a star more than a planet, glowing with molten brilliance across its entire surface. This comparison is vital, because by studying Io, we gain a window into our own planet's fiery past, seeing in its constant eruptions a reflection of what Earth endured on a much larger scale. And yet the difference between Io and Earth is what determined our fate. Io has remained a fire world for billions of years, lifeless and sterile, while Earth cooled just enough, stabilized just enough to allow water to condense, oceans to form, and life to emerge. Thus, he serves as a haunting reminder of what Earth could have been had its fire never subsided, a permanent hellscape locked in volcanic fury. And it is precisely the balance between fire and cooling, between destruction and stability, that made Earth. For our world was forged in the same crucible of lava, but did not remain imprisoned there forever, instead transforming its fiery scars into fertile ground. At the heart of Earth's fiery transformation lay the chemistry of molten rock itself. For magma is not a uniform substance, but a complex mixture of silicates, metals, and volatiles that change as they melt, crystallize, and flow. And in early Earth's magma oceans, this chemical alchemy unfolded on a planetary scale, with minerals constantly crystallizing and sinking or floating depending on their density, creating the first true separation of layers in the planet's body. Heavier minerals rich in iron and magnesium sank into the mantle or even toward the core, while lighter minerals rich in silicon and aluminum rose to the surface, forming crustal material. And in this ceaseless differentiation process, Earth created not only the physical architecture of crust, mantle, and core, but also the geochemical diversity that would allow oceans, atmospheres, and eventually life. Volcanic gases like carbon dioxide and sulfur dioxide interacted with water vapor to shape the greenhouse effect, while trace amounts of phosphorus, nitrogen, and other compounds entered circulation through eruptions, seeding the environment with essential ingredients for biology. Thus, the chemistry of fire was the chemistry of creation, and though to us a volcano seems merely destructive, in reality each eruption was a chemical experiment conducted on a planetary scale, endlessly remixing the elements of Earth and preparing them for future complexity, so that fire, deep beneath the seething surface, an even greater transformation was underway, as Earth's molten state allowed iron and nickel to sink toward the center, creating the metallic core that remains the heart of our planet today. And this process, known as planetary differentiation, was one of the most important events in Earth's history, for it established the structure that would govern all future geology and biology, and most importantly, it gave birth to Earth's magnetic field, a shield generated by the convection of liquid iron in the outer core, protecting the planet from the solar wind and cosmic radiation. Without this shield, the atmosphere would have been stripped away as happened on Mars, and Earth would have remained barren. But because the fiery beginning allowed heavy metals to sink and the core to form, Earth gained a defense system that has safeguarded its habitability ever since. The core also acted as a heat engine, driving convection in the mantle and sustaining the volcanic and tectonic processes that keep Earth geologically alive, meaning that from the very heart of fire came the conditions for stability and protection. So when we imagine the early Earth glowing like a star, we should remember that this fire was not mere chaos, for within it the metallic heart of the planet was forged, and in that heart lay the future of oceans, air, and life itself, showing again how destruction and creation are so inseparable in the story of our world. From this fiery foundation, Earth slowly began to cool just enough to allow water to emerge, and this moment marked one of the greatest transitions in planetary history, when the world of fire gave way to the world of oceans, for as steam in the atmosphere condensed into rain, it fell in torrents upon the still glowing crust, only to hiss and evaporate instantly, creating storms of boiling vapor that raged for millennia, until at last enough cooling occurred that water could remain on the surface, filling the first basins with oceans that still steamed with volcanic heat. These were not calm blue seas, but turbulent cauldrons boiling at the edges, their waves constantly interacting with lava flows and eruptions. Yet their presence marked the beginning of a new Earth, one where water and fire coexisted in a dynamic balance. The arrival of liquid water also accelerated chemical reactions on the surface, dissolving minerals, circulating through cracks, and interacting with volcanic gases, creating complex chemical soups that would one day nurture life. Thus, the transition from a purely fiery planet to a water-bearing one was not an end to the fire, but a new stage of interplay, where lava and ocean, eruption and storm, combined in ways that would sculpt the destiny of Earth forever. And so from fire's destruction was born the cooling breath of water, the companion that would tame the inferno into fertility. The question of where Earth's water came from has long been debated, and many scientists believe that comets and water-rich asteroids delivered much of it during the same period of bombardment that once covered Earth in fire, meaning that water itself may have been a gift from the heavens, arriving in icy projectiles that slammed into the molten planet, vaporizing on impact but gradually adding to the steam that thickened the atmosphere until it could condense into rain. In this way, destruction once again carried the seeds of creation, for the very same impacts that devastated Earth with fire and fury may also have filled it with the essential liquid that would sustain oceans and life. And it is remarkable to imagine that every drop of water in our seas, lakes, and rivers, and even in our bodies, may once have been carried on asteroids or comets billions of years ago, delivered through fire into the crucible of Earth. Thus, the origin of water is intertwined with the story of fire, because without the fiery impacts that melted the crust and allowed out gassing, the atmosphere could not have trapped steam, and without the bombardment delivering ice, there might never have been enough water to form oceans. So once again, we see that fire and water are not opposites, but partners in the grand creation of Earth, locked in an eternal dance that has shaped our world from the very beginning. When fire and water finally met on the surface of Earth, the result was a scene of unimaginable chaos and grandeur, for rain poured endlessly upon molten landscapes, creating explosions of steam where droplets touched lava, and entire rivers of water boiled away upon contact with basaltic plains. While vast clouds of vapor rose to the skies, fueling more storms and perpetuating the cycle, this was not the calm balance of modern Earth, but an era of violent interaction, where water tried to cool and tame the fire but was constantly overwhelmed. Yet slowly, over millions of years, the balance shifted and water gained the upper hand, filling basins faster than eruptions could boil them dry, creating permanent oceans that still steamed and boiled at their edges, but endured nonetheless. This epic struggle between fire and water shaped the surface into a patchwork of continents and seas, where lava flows met ocean waves, creating new minerals at their boundaries, and hydrothermal systems circulated hot water through the crust, leaching elements and creating chemical gradients that would prove essential for life. In this interplay, fire provided the energy and water the medium, and together they created a dynamic system capable of producing complexity, so that the world, once nothing but flame, now became a cauldron of fire and ocean, destruction and fertility side by side, a paradoxical landscape where hell and hope coexisted. Out of this fiery water world, the foundations of plate tectonics slowly began to emerge. For as the crust thickened and cooled, it fractured into segments that floated atop the still convective mantle, and the immense heat below drove these plates to move, collide, and reshape the surface. Initiating the long geological dance that continues to this day, early tectonic movements were far more violent than modern ones, with plates crashing together and tearing apart in cycles of destruction, and the constant upwelling of magma at ridges and subduction of crust into the mantle created a self-renewing system that recycled materials and ensured the planet's surface remained dynamic. This tectonic activity, born from fire, was one of Earth's greatest gifts because it not only created continents and mountain ranges, but also maintained the carbon cycle, regulating the atmosphere and climate over billions of years, making long-term habitability possible. Without plate tectonics, Earth might have become a stagnant, lifeless world like Venus or Mars, but because the fiery engine of the mantle continued to churn and crack the crust, the surface remained fertile and dynamic, capable of supporting oceans, ecosystems, and civilizations. Thus, plate tectonics, terrifying in its power, was also the ultimate expression of fire's constructive force, proving once again that Earth's inferno was not only destruction, but also the engine of renewal. Perhaps the most astonishing outcome of Earth's fiery youth is that the very same volcanic systems that once covered the planet in oceans of lava later became the cradles of life, for around hydrothermal vents on the early ocean floor, where magma heated seawater into superheated fluids, rich in minerals, chemical gradients were created that could fuel the first living systems, and many scientists now believe that life itself may have originated in such fiery environments, where water and fire met in intimate embrace. These vents spewed not only heat, but also compounds like hydrogen sulfide, iron, and carbon dioxide, and within their mineral chimneys, organic molecules may have formed and combined into the first self-replicating systems, protected from the chaotic surface by the ocean above. It is poetic to think that fire, once the enemy of stability, became the mother of biology, providing the energy and chemistry needed for life to spark, and that Earth's fiery heart, instead of condemning the planet to eternal sterility, in fact, ensured its fertility. Thus, when we trace our lineage back to its roots, we find ourselves children of fire as much as of water, for without the volcanoes, magma, and hydrothermal systems of early Earth, there might never have been the spark of life, and the fiery world we call lava Earth would have remained forever barren. And so, from a beginning of chaos and flame, from a world where skies burned with lightning and the surface boiled in molten seas, Earth transformed itself into a sanctuary of oceans, continents, and life, carrying within every mountain, every forest, and every living being the memory of its fiery youth. For even today, volcanoes still erupt, lava still flows, and the planet's core still burns, reminders that beneath the calm surface, the heart of fire continues to beat, And this truth gives our world its vitality, its protection, and its beauty, showing that destruction and creation are not enemies but partners in the grand story of existence. And as we gaze up at the moon, born of an ancient impact, or watch the sun set over oceans that were once steam rising from volcanic skies, we can see how far the planet has traveled from its days as a furnace, yet also how deeply we remain connected to that inferno, for without it there would be no water, no air, no land, and no life, and thus the tale of Lava Earth is not one of doom but of transformation. A reminder that even in fire there is hope, and that the most violent beginnings can give rise to the most extraordinary destinies. The magnetic field dynamics of early Earth during the lava world phase represent one of the most complex and poorly understood aspects of planetary evolution, with implications that extend far beyond simple geophysical curiosity. During the Hadean Eon, when Earth's surface remained largely molten, the planet's magnetic field was likely undergoing dramatic and rapid changes that would have profoundly affected both the retention of the early atmosphere and the planet's interaction with the solar wind. The generation of Earth's magnetic field, known as the geodynamo, depends on convective motion within the liquid outer core, but during the lava world, the thermal structure of the planet was so different from today that the magnetic field generation process would have operated under entirely different conditions. The core formation process, which involved the segregation of iron and nickel from silicate materials, was still actively occurring during much of the Hadean Eon, meaning that the size, composition, and thermal state of the core were constantly evolving. This dynamic core formation process would have created highly variable magnetic field strengths and orientations, potentially leading to frequent magnetic reversals or even complete temporary cessations of the magnetic field. The implications of these magnetic field variations were enormous, as the magnetic field serves as a crucial shield protecting the planet's atmosphere from being stripped away by the solar wind. During periods when the magnetic field was weak or absent, the intense solar radiation and particle bombardment that characterized the early solar system could have eroded significant portions of Earth's early atmosphere, forcing the planet to rebuild its atmospheric envelope through continued volcanic outgassing. The molten surface conditions also meant that there were no solid rocks available to record the magnetic field orientation, making it extremely difficult for modern scientists to reconstruct the magnetic history of this period. However, some clues can be gleaned from studying the oldest surviving minerals and from theoretical models of core formation and thermal evolution. The relationship between magnetic field strength and atmospheric retention during the lava world phase may have been one of the crucial factors determining whether Earth would successfully transition to a habitable planet or remain permanently hostile to life. Highlighting the interconnected nature of planetary systems and the multiple factors that must align for habitability to emerge, the role of tidal forces and Earth-Moon interactions during the lava world phase adds another layer of complexity to understanding our planet's early thermal and geological evolution. The Moon, which likely formed from debris created by the giant impact of a Mars-sized object with Earth, was initially much closer to our planet than it is today, creating tidal forces that were orders of magnitude stronger than those we experience in the modern world. These intense tidal forces would have caused significant flexing and heating of Earth's crust and upper mantle, contributing additional energy to maintain the molten surface conditions that characterize the lava world phase. The tidal heating effect was particularly pronounced because the early Earth-Moon system had not yet reached the synchronized rotation state that exists today, meaning that the tidal bulges were constantly moving across Earth's surface, generating friction and heat through the deformation of rock and magma. This process, similar to what we observe today on Jupiter's moon Io, would have created zones of particularly intense volcanic activity at the points where tidal stresses were great, potentially leading to the formation of massive volcanic complexes that dwarfed anything seen in more recent geological periods. The tidal interactions also affected the length of Earth's day, which was much shorter during the Hadean Eon, possibly lasting only 5-6 hours compared to the 24-hour day we experience today. This rapid rotation would have created strong Coriolis effects that influenced atmospheric and oceanic circulation patterns, potentially affecting how heat was distributed around the planet and influencing the rate at which different regions cooled from their molten state. The gravitational interactions between Earth and the Moon also caused the Moon to gradually spiral outward from its initial position, reducing the tidal heating effect over time and contributing to the eventual cooling of Earth's surface. However, the process was gradual, occurring over hundreds of millions of years, meaning that tidal heating remained a significant factor in maintaining molten surface conditions throughout much of the Hadean Eon. Understanding these tidal interactions is crucial for reconstructing the thermal evolution of early Earth and for understanding how the Earth-Moon system evolved into its current configuration. The study of tidal heating also has implications for understanding the evolution of other planetary systems, particularly those with large moons or close-orbiting companions that might experience similar effects. The atmospheric composition and dynamics during Earth's lava world phase created a greenhouse environment so extreme that it challenges our understanding of planetary climate systems and atmospheric physics. The early atmosphere was not only incredibly dense with pressures potentially exceeding 100 times the current atmospheric pressure, but it was also dominated by greenhouse gases that created a thermal trap of unprecedented efficiency. Water vapor, which can be an extremely potent greenhouse gas under the right conditions, likely made up a significant fraction of the early atmosphere, creating what atmospheric scientists call a moist greenhouse or runaway greenhouse effect. So, in this state, the atmosphere becomes so saturated with water vapor that additional heating leads to more evaporation, which creates more greenhouse heating, establishing a positive feedback loop that can maintain extremely high temperatures indefinitely. Carbon dioxide, sulfur dioxide, and other volcanic gases contributed additional greenhouse heating, while the high atmospheric pressure increased the efficiency of heat retention through pressure broadening effects that expanded the absorption spectra of greenhouse gases. The atmospheric dynamics under these extreme conditions would have been unlike anything observed on modern Earth, with convection patterns that could transport enormous amounts of heat and moisture vertically through the dense atmosphere. The high atmospheric density would have also created surface pressures similar to those found in the deep ocean today, but filled with superheated gas rather than liquid water. Lightning activity would have been intense and nearly constant, generated by the vigorous convection and the abundance of condensing water vapor and volcanic particles in the atmosphere. The atmospheric composition was also highly reducing, meaning it contained very little free oxygen and instead was dominated by hydrogen-rich compounds that would readily react with any oxygen that might be produced through photochemical processes. This reducing atmosphere had important implications for the chemistry of the surface and near-surface environment, as it determined which types of minerals could form and remain stable under the prevailing conditions. The transition away from this extreme greenhouse atmosphere was one of the most crucial steps in Earth's evolution toward habitability, requiring not only cooling of the surface, but also fundamental changes in atmospheric composition and dynamics that would take hundreds of millions of years to complete. The development of the first primitive hydrological cycle during the waning phases of the lava world epoch represents one of the most significant transitions in Earth's surface processes, marking the beginning of the complex water cycle that continues to shape our planet today. As surface temperatures began to drop below the critical point of water, the planet experienced the first tentative formation of liquid water bodies. But these early attempts at establishing a stable hydrosphere were fraught with instability and constant disruption from ongoing volcanic activity and impact events. The first liquid water likely appeared in isolated pools in topographic depressions, such as impact craters or volcanic calderas, where local cooling or shielding effects created conditions marginally suitable for water condensation. However, these early water bodies existed in a constant state of tension with the still extreme surface conditions, often lasting only briefly before being vaporized by renewed volcanic activity or fresh impact events. So, the water that did manage to persist was extremely hot, often approaching the boiling point, and was heavily laden with dissolved minerals and volcanic gases that made it highly acidic and chemically aggressive. This early water interacted vigorously with the surrounding volcanic rocks, initiating the first large-scale weathering processes and beginning the slow transformation of Earth's surface chemistry that would eventually create more moderate conditions. The primitive hydrological cycle that began to develop during this period was dominated by rapid evaporation and condensation processes, creating intense precipitation events that could temporarily flood large areas with scalding, mineral-rich water. The high atmospheric pressure meant that water could remain liquid at much higher temperatures than would be possible under modern conditions, allowing liquid water to exist even in environments that would be instantly lethal by today's standards. The interaction between the emerging hydrosphere and the still active volcanic systems created unique geological processes, including the formation of pillow lavas where volcanic eruptions occurred underwater, and the development of hydrothermal systems that concentrated and redistributed chemical elements in ways that would have important implications for the eventual emergence of life. The establishment of even this primitive hydrological cycle represented a fundamental shift in Earth's surface energy balance, as the high heat capacity of liquid water began to moderate temperature fluctuations, and the evaporation and condensation of water began to transport heat more efficiently than purely atmospheric processes could achieve alone. The geochemical evolution of Earth's early crust during the transition away from the lava world phase involved complex processes of differentiation, recycling, and chemical evolution that established many of the fundamental characteristics of our planet's outer layer. The first stable crustal rocks to form were compositionally quite different from the continental and oceanic crusts that dominate Earth's surface today, reflecting the unique conditions under which they crystallized from the global magma ocean. These early crustal rocks were likely ultramafic in composition, meaning they were rich in magnesium and iron-bearing minerals like olivine and pyroxene, and they formed under conditions of extreme temperature and pressure that are rarely encountered in modern geological processes. The process of crustal formation was not a simple matter of cooling and solidification. Instead, it involved complex fractional crystallization processes where different minerals formed and separated from the magma at different temperatures, creating layered sequences of rocks with varying compositions and properties. As these early crustal rocks began to accumulate and thicken, they underwent further modification through processes of partial melting, metamorphism, and chemical alteration that gradually transformed their composition toward the more evolved, silica-rich compositions that characterize modern continental crusts. The interaction between the emerging crust and the hot, chemically aggressive early atmosphere and hydrosphere led to intense weathering processes that broke down primary minerals and created new secondary minerals better suited to surface conditions. These weathering processes also began the first primitive cycles of erosion, transport, and deposition that would eventually lead to the formation of sedimentary rocks and the complex geological processes that shape Earth's surface today. The early crust was also constantly being modified by continued volcanic activity, which added new material from below while simultaneously remelting and recycling existing crustal rocks back into the mantle. This crustal recycling process was much more efficient during the Hadean eon than it is today due to the higher heat flow and more vigorous convection in Earth's interior, meaning that very little of the original Hadean crust has survived to the present day. The chemical evolution of the early crust also involved the concentration and redistribution of trace elements and rare metals that would later become important for biological processes, setting the stage for the eventual emergence of life by creating the geochemical environment in which complex biochemistry could develop. The transition from global volcanic activity to more localized and episodic eruptions marked a crucial phase in Earth's evolution away from its lava world origins, representing a fundamental shift in the planet's thermal regime and geological processes. During the peak of the lava world phase, volcanic activity was essentially continuous and planet-wide, with vast regions of the surface simultaneously erupting or remaining in a molten state. However, as Earth's internal heat production gradually declined and the rate of heat loss to space increased, volcanic activity began to become more concentrated in specific regions and less constant over time. This transition was not uniform or sudden. Instead, it occurred gradually over hundreds of millions of years as different regions of the planet cooled at different rates depending on their geological setting and proximity to major heat sources. The areas that cooled first became the nuclei of the first stable continental masses, while regions with higher heat flow continued to experience intense volcanic activity for much longer periods. The concentration of volcanic activity into specific zones also led to the development of the first primitive forms of plate tectonics, as differential cooling created density contrasts that drove the first large-scale movements of crustal materials. These early tectonic processes were much more vigorous and rapid than modern plate tectonics, driven by the higher heat flow and more vigorous convection that characterized Earth's interior during this period. The transition to more localized volcanism also changed the nature of volcanic eruptions themselves, as the formation of stable crust allowed for the development of volcanic edifices and the accumulation of volcanic products in specific locations rather than being constantly mixed back into the global magma ocean. This led to the formation of the first large shield volcanoes and volcanic complexes, some of which may have rivaled or exceeded the size of modern features like the Hawaiian volcanic chain or the Yellowstone caldera system. The more episodic nature of volcanic activity also meant that there were periods of relative quiescence when the surface could cool and stabilize, allowing for the formation of more complex geological structures and the beginning of processes like erosion and sedimentation. However, even during these quieter periods, the volcanic systems remained far more active than anything observed in recorded human history, and major eruptions could still temporarily return large regions to a molten state. The study of this transitional period is challenging because the geological record from this time is poorly preserved, but it represents a crucial phase in Earth's evolution that set the stage for all subsequent geological and biological development. The formation and evolution of Earth's early atmosphere during the lava world phase involved complex interactions between volcanic outgassing, atmospheric escape, and chemical reactions that ultimately determined whether our planet would develop conditions suitable for life. The primary atmosphere that Earth may have captured during its initial formation was likely composed mainly of hydrogen and helium derived from the solar nebula, But this light, hydrogen-rich atmosphere was probably lost relatively quickly due to the high temperatures and intense solar radiation that characterized the early solar system. So, the secondary atmosphere that developed to replace it was created entirely through volcanic outgassing, as the constant eruptions and degassing of magma released enormous quantities of water vapor, carbon dioxide, sulfur compounds, nitrogen, and various other gases from Earth's interior. The composition of this volcanic atmosphere was determined by the chemical equilibrium between the magma and the overlying gas phase, which in turn depended on factors like temperature, pressure, and the oxidation state of the magma. During the earliest phases of atmospheric development, when surface temperatures were at their highest, the atmosphere was dominated by water vapor and carbon dioxide, creating an extremely dense greenhouse atmosphere that trapped heat and maintained the molten surface conditions. As volcanic activity continued over millions of years, the atmospheric composition gradually evolved as different volcanic processes contributed different gas mixtures and as chemical reactions in the atmosphere began to modify the original volcanic gases. The high temperature conditions also led to extensive photochemical reactions in the upper atmosphere, where solar ultraviolet radiation broke apart molecular bonds and created new chemical compounds that would not have been stable under cooler conditions. The atmospheric pressure during this period was likely much higher than today's atmospheric pressure, possibly by factors of tens to hundreds, creating surface conditions that were more similar to those found in the deep ocean than to modern surface conditions. The dense atmosphere also had important implications for heat transport and climate, as the high pressure and density allowed for very efficient convective heat transfer that could redistribute thermal energy around the planet much more effectively than is possible under modern atmospheric conditions. The evolution of atmospheric composition was also influenced by impact events, which could temporarily strip away portions of the atmosphere or contribute additional gases through the vaporization of impacting bodies. Understanding the evolution of Earth's early atmosphere is crucial for comprehending how the planet eventually developed conditions suitable for liquid water and life. And it provides important insights into the atmospheric evolution of other planets both within our solar system and around other stars. The role of organic chemistry during Earth's lava world phase presents one of the most intriguing and controversial aspects of early Earth science, as it addresses the fundamental question of how the building blocks of life could have survived or been synthesized under such extreme conditions. While the surface temperatures and chemical conditions that prevailed during most of the Hadean eon would have been immediately destructive to most organic compounds, recent research has suggested that certain protected environments and specific chemical processes might have allowed for the synthesis and preservation of simple organic molecules, even during this hellish period. The volcanic outgassing processes that dominated the early Earth released not only water vapor and carbon dioxide, but also significant quantities of reduced carbon compounds such as methane, carbon monoxide, and hydrogen sulfide, providing the raw materials from which more complex organic molecules could potentially be synthesized. The high temperature, high pressure conditions that existed in certain subsurface environments, particularly in hydrothermal systems where hot water interacted with mineral-rich volcanic rocks, may have provided the energy and chemical conditions necessary for the formation of simple organic compounds through processes similar to those observed in modern hydrothermal vents. Laboratory experiments have shown that amino acids, the building blocks of proteins, can be synthesized under conditions similar to those that may have existed in early Earth's hydrothermal systems, suggesting that the basic chemistry of life may have begun even during the waning phases of the lava world epoch. The interaction between organic compounds and mineral surfaces also played a crucial role, as certain minerals can catalyze organic reactions and provide protective surfaces that shield organic molecules from destruction by high temperatures or reactive atmospheric gases. Iron-sulfur minerals, which would have been abundant in the early Earth's volcanic environments, are particularly effective at catalyzing organic reactions and may have served as primitive metabolic systems that prefigured the more complex biochemistry that would later evolve in living organisms. The constant recycling of crustal materials through volcanic processes also provided opportunities for organic compounds to be concentrated and modified through repeated heating and cooling cycles, potentially leading to the formation of more complex molecular structures over geological timescales. However, the survival and evolution of organic compounds during the lava world phase would have required very specific conditions and protection mechanisms. And it remains unclear whether significant quantities of complex organic molecules could have accumulated during this period, or whether the emergence of life required the more moderate conditions that developed only after the end of the lava world phase. The impact history of early Earth during the lava world phase represents one of the most violent and chaotic periods in our planet's history, with bombardment rates and impact energies that dwarf anything experienced during more recent geological periods. The early solar system was filled with debris left over from planetary formation, including asteroids, comets, and planetesimals ranging in from small rocky fragments to objects hundreds of kilometers in diameter. Earth's position in the inner solar system made it a natural target for this cosmic debris, and the planet experienced a constant barrage of impacts that contributed both material and energy to the growing world. The largest impacts during this period were truly catastrophic events that could have global consequences, temporarily or permanently altering Earth's thermal evolution and surface conditions. The impact that likely created the Moon, involving a Mars-sized object called Theia, represents the extreme end of this impact spectrum and would have essentially reset Earth's thermal evolution by returning much of the planet to a completely molten state. However, even smaller impacts during the late heavy bombardment period could create temporary magma seas hundreds of kilometers in diameter and maintain molten conditions across vast regions for thousands of years. The energy released by these impacts was enormous, with the largest events releasing energy equivalent to billions of nuclear weapons and creating temperatures and pressures that could vaporize rock and temporarily strip away portions of the atmosphere. The impact process also contributed to Earth's bulk composition by adding material from various sources throughout the solar system, including water-rich comets that may have contributed significantly to Earth's eventual water inventory. The bombardment history was not uniform over time. Periods of intense bombardment alternated with relatively quieter intervals, creating cycles of heating and cooling that influenced the planet's overall thermal evolution. The impact cratering process also created the first significant topographic relief on Earth's surface, as large impact craters provided basins where magma could accumulate and differentiate, potentially accelerating the process of crustal formation and chemical evolution. The study of impact processes during the early Earth is complicated by the fact that virtually no direct geological evidence from this period has survived to the present day. But the heavily cratered surfaces of the Moon and other bodies provide crucial information about the timing, frequency, and intensity of early solar system bombardment. Understanding the impact history of early Earth is essential for reconstructing the conditions under which life eventually emerged, and for understanding the role that cosmic catastrophes played in shaping our planet's early evolution. The thermal evolution of Earth's interior during the lava world phase involved complex processes of heat generation, transport, and loss that determined how long the planet remained in a molten state and how it eventually evolved toward more stable, differentiated conditions. The primary sources of heat during this period included the gravitational potential energy released during planetary accretion, the kinetic energy of impact events, and the radioactive decay of unstable isotopes that were much more abundant in the early solar system than they are today. The short-lived radioactive isotopes, particularly aluminum, 26 and iron-60, provided enormous amounts of heat during the first few million years of Earth's existence, contributing to the melting and differentiation processes that established the planet's layered structure. The heat generated by these various sources was so intense that it maintained a global magma ocean for hundreds of millions of years, with convective circulation patterns that transported heat from the interior to the surface, where it could be radiated away into space. The cooling rate of this system was controlled by the balance between heat generation and heat loss, with the efficiency of heat transport through the magma ocean playing a crucial role in determining how quickly the planet could begin to solidify. The high temperatures also drove vigorous convection in Earth's interior, creating circulation patterns that were much more rapid and energetic than those observed in the modern mantle. This vigorous convection was crucial for the differentiation process that separated Earth's core, mantle, and crust, as it provided the mechanism for transporting denser materials toward the center and lighter materials toward the surface. The thermal evolution of the interior also influenced surface processes through its control of volcanic activity and heat flow, with higher internal temperatures driving more intense and widespread volcanism that contributed to maintaining molten surface conditions. As the internal heat sources gradually declined and the efficiency of heat loss increased, the planet began a slow transition toward more stable thermal conditions. But this process took hundreds of millions of years and was repeatedly interrupted by large impact events that could temporarily reheat the interior. The study of Earth's early thermal evolution relies heavily on theoretical models and laboratory experiments, as direct geological evidence from this period is extremely rare. But understanding these processes is crucial for comprehending how Earth evolved from a molten ball of rock into the differentiated, habitable planet we know today. The development of Earth's first stable land masses during the waning phases of the lava world epoch represents a crucial transition in planetary evolution, marking the beginning of the complex geological processes that would eventually shape the continents and ocean basins we see today. The formation of stable continental crust was a gradual process that required the accumulation and preservation of low-density, silicate-rich rocks that could resist recycling back into the mantle through tectonic processes. The first protocontinents were likely small, isolated masses of thickened crust that formed through the partial melting and differentiation of earlier crustal materials, creating rocks that were progressively enriched in lighter elements like silicon, aluminum, and potassium. Foam. These early continental nuclei were constantly threatened by the high heat flow and vigorous tectonic activity that characterized the Hadean Eon. And many early attempts at continental formation were probably destroyed and recycled before they could establish permanent footholds on the surface. The growth of stable continental masses occurred through a combination of volcanic addition, where new crustal material was added from below through continued eruptions, and lateral accretion, where smaller crustal fragments were welded together through tectonic collisions. The development of continental crust also involved complex processes of crustal reworking, where existing rocks were repeatedly melted, metamorphosed, and recrystallized under changing temperature and pressure conditions. them, gradually evolving toward the more evolved compositions that characterize modern continental rocks. The formation of stable continents was closely linked to the development of the first primitive forms of plate tectonics, as the lateral movement and collision of crustal fragments provided the mechanism for continental growth and consolidation. However, these early tectonic processes were much more rapid and intense than modern plate tectonics, driven by the higher heat flow and more vigorous convection that existed during this period. The emergence of stable land masses had profound implications for Earth's surface processes as they provided platforms for the development of terrestrial weathering processes, created topographic relief that could influence atmospheric and oceanic circulation patterns. The continental masses also served as repositories for crustal materials that might otherwise have been recycled back into the mantle, allowing for the preservation of increasingly complex geological structures and the gradual accumulation of the thick, stable continental crust that would eventually support terrestrial life. Understanding the processes of early continental formation is challenging because very little geological evidence from this period has survived to the present day. But the study of the oldest surviving crustal rocks and theoretical models of crustal evolution provide important insights into how Earth's first stable landmasses developed from the chaos of the lava world phase. The interaction between Earth's emerging hydrosphere and the still active volcanic systems during the transition away from the lava world created unique geological processes and chemical reactions that had profound implications for the planet's continued evolution toward habitability. When liquid water first began to accumulate in stable bodies on Earth's surface, it encountered a landscape dominated by hot volcanic rocks and active lava flows, creating violent interactions that generated enormous quantities of steam and initiated the first large-scale weathering processes. The reaction between hot lava and water, known as explosive volcanism or phreatomagmatic eruptions, created some of the most violent geological processes imaginable, as the rapid conversion of water to steam generated explosive pressures that could fragment lava into fine particles and propel volcanic debris over vast distances. These water-magma interactions also created unique types of volcanic rocks, including pillow lavas formed when eruptions occurred underwater and hyaloclastite breccias formed when explosive interactions between water and lava created chaotic mixtures of volcanic fragments and altered minerals. The chemical interaction between water and hot volcanic rocks initiated intense hydrothermal processes that leached elements from the rocks and concentrated them in solution, creating the first mineral-rich hot springs and hydrothermal systems that would later prove crucial for the development of early life. The high temperatures and chemically aggressive nature of these early hydrothermal systems created conditions unlike anything observed on modern Earth, with water temperatures approaching or exceeding the boiling point and chemical compositions that included high concentrations of dissolved metals, sulfur compounds, and other elements that would be toxic under normal conditions. However, these extreme hydrothermal environments also provided the energy gradients and chemical diversity that may have been necessary for the first primitive metabolic processes to develop. As the reaction between hot water and mineral surfaces created opportunities for energy extraction that could support simple forms of chemosynthetic metabolism. The circulation of heated water through volcanic rocks also began the process of hydrothermal alteration, where the original minerals in volcanic rocks were replaced by new minerals that were more stable under the prevailing conditions, creating assemblages of altered rocks that recorded the temperature and chemical conditions of these early Earth environments. The development of these water-rock interaction processes marked a fundamental shift in Earth's surface chemistry, as they initiated the complex cycles of weathering, erosion, transport, and deposition that continue to shape our planet's surface today. Understanding these early hydrothermal processes is crucial for reconstructing the conditions under which life may have first emerged and for understanding how Earth's surface environment evolved from the sterile, molten conditions of the lava world toward the more hospitable conditions that would eventually support complex ecosystems. The atmospheric chemistry of Earth during the lava world phase involved complex networks of chemical reactions that determined not only the composition of the early atmosphere, but also the rate at which the planet could cool and transition toward more habitable conditions. The volcanic gases that dominated the early atmosphere were not simply inert components. Instead, they participated in elaborate photochemical reaction networks driven by intense solar ultraviolet radiation that could penetrate the dense, steam-laden atmosphere. Water vapor, which made up a large fraction of the early atmosphere, underwent photodissociation in the upper atmosphere, where high-energy solar radiation broke apart water molecules into hydrogen and oxygen atoms. The light hydrogen atoms could escape to space relatively easily, while the heavier oxygen atoms were more likely to remain in the atmosphere where they could participate in oxidation reactions with other atmospheric constituents. This process of hydrogen escape was crucial for the eventual evolution of Earth's atmosphere toward more oxidizing conditions. But during the lava world phase, the oxygen produced by water photodissociation was quickly consumed by reactions with reduced volcanic gases like hydrogen sulfide, sulfur dioxide, and carbon monoxide. The sulfur chemistry of the early atmosphere was particularly complex, involving multiple oxidation states of sulfur and creating compounds like sulfur dioxide, hydrogen sulfide, and various sulfur aerosols that could influence the atmospheric energy balance by absorbing and scattering solar radiation. Carbon chemistry was also important, with carbon dioxide serving as a major greenhouse gas, while carbon monoxide and methane provided additional sources of reduced carbon that could participate in complex atmospheric reactions. The high atmospheric pressure and temperature during this period meant that many chemical reactions that would be kinetically slow under modern conditions could proceed rapidly, creating opportunities for the formation of complex organic and inorganic compounds that might not be stable under cooler conditions. The atmospheric chemistry was also strongly influenced by the interaction between the atmosphere and the molten surface, as volatile elements could dissolve in and exsolve from magma depending on temperature and pressure conditions, creating feedback loops between surface and atmospheric processes. And atmospheric. Lightning, which was probably extremely common in the turbulent, steam-laden early atmosphere, provided additional energy for chemical reactions and may have been an important source of fixed nitrogen compounds that could serve as nutrients for early biological processes. The study of early atmospheric chemistry relies heavily on theoretical models and laboratory experiments, as direct evidence of atmospheric composition from this period is extremely limited. But understanding these processes is crucial for comprehending how Earth's atmosphere evolved from its early, highly reduced state toward the more oxidizing conditions that would eventually support oxygen-producing photosynthesis and complex life. The mineralogical evolution of Earth's surface during the transition away from the lava world involved the formation and transformation of mineral assemblages under conditions that were unique in our planet's history, creating rock types and mineral associations that provide crucial clues about the extreme environments that characterized early Earth. The first minerals to crystallize from the global magma ocean were likely high-temperature phases such as olivine, pyrozine, and plagioclase feldspar, which form the primary constituents of ultramafic and mafic igneous rocks. However, the continued high temperatures and chemically aggressive atmospheric and hydrospheric conditions meant that these primary minerals were constantly being altered and replaced by secondary minerals that were more stable under the prevailing surface conditions. The interaction between hot volcanic rocks and the emerging hydrosphere created extensive hydrothermal alteration zones, where primary minerals were replaced by hydrated phases such as serpentine minerals, chlorites, and various clay minerals that incorporated water into their crystal structures. These alteration processes were much more intense and widespread than anything observed in modern geological settings, creating thick zones of altered rock that extended for kilometers below the surface in some areas. The chemical conditions during this period also favored the formation of unusual mineral assemblages that are rarely observed in younger rocks, including high-temperature, hydrated minerals, and exotic phases that formed under the unique pressure and temperature conditions that existed during the transition from molten to solid surface condition. Iron-bearing minerals were particularly important during this period, as the reducing conditions that prevailed in the early atmosphere and hydrosphere favored the formation of iron sulfide minerals such as pyrite and pyrrhotite, which would later serve as important sources of energy for early chemosynthetic organisms. The formation of the first sedimentary minerals also began during this period as the intense weathering of volcanic rocks produced the first clays, quartz, and other detrital minerals that could be transported and deposited by the emerging hydrological systems. However, these early sedimentary processes operated under conditions that were vastly different from modern surface environments, with much higher temperatures, more aggressive chemical weathering, and rapid rates of erosion and deposition that created sedimentary sequences unlike anything formed in more recent geological periods. The preservation of minerals from this early period is extremely rare, as most early crustal rocks have been destroyed by subsequent geological processes. But the few surviving examples provide invaluable information about the conditions that existed during Earth's transition from a lava world to a more stable, differentiated planet. Lange. The study of early mineral assemblages also has important implications for understanding the geochemical cycles that operated during this period and for reconstructing the chemical evolution of Earth's surface environment as it progressed toward conditions that could eventually support life. The energetics of Earth's lava world phase involved the complex interplay of multiple heat sources and heat loss mechanisms that determined how long the planet remained in a molten state and how it eventually evolved toward thermal equilibrium with space. The primary energy sources during this period included the gravitational potential energy released during planetary accretion, which converted the kinetic energy of infalling planetesimals into heat through impact processes and gravitational compression. The accretional heating was supplemented by the energy released through core formation, as dense metallic materials segregated from silicate materials and sank toward the center of the planet, releasing enormous amounts of gravitational potential energy in the process. Radioactive decay provided another crucial energy source, with short-lived isotopes like aluminum-26, iron-60, and hafnium-182 contributing enormous amounts of heat during the first few million years of Earth's existence. These short-lived isotopes were much more abundant in the early solar system than they are today, having been produced by supernova explosions that occurred shortly before the formation of our solar system. And their rapid decay provided the energy necessary to melt and differentiate the terrestrial planets. Impact heating continued to be important throughout the Hadean Eon as the continued bombardment of Earth by asteroids and comets added both kinetic energy and material to the growing planet. The largest impacts could temporarily increase the global heat budget by enormous amounts, potentially remelting entire hemispheres and extending the duration of molten surface conditions by millions of years. The balance between these various heat sources and the mechanisms of heat loss determine the overall thermal evolution of the planet. Heat loss occurred primarily through radiation from the surface, but the efficiency of this process was strongly influenced by atmospheric properties such as density, composition, and opacity. The dense, steam-laden early atmosphere was extremely effective at trapping heat through greenhouse effects, greatly reducing the rate at which heat could be lost to space and contributing to the maintenance of high surface temperatures for extended periods. Convection in the magma ocean provided the primary mechanism for transporting heat from the interior to the surface, with circulation patterns that were much more vigorous than those observed in the modern solid mantle. The efficiency of convective heat transport was crucial for determining how quickly the planet could cool, as it controlled the rate at which heat generated in the interior could reach the surface, where it could be radiated away. Understanding the energetics of early Earth is essential for reconstructing the planet's thermal history and for understanding how the various factors that influence planetary evolution interact to determine whether a planet will successfully transition from molten conditions to a stable, potentially habitable state. The geodynamic processes operating during Earth's lava world phase were fundamentally different from modern plate tectonics, involving more rapid and vigorous circulation patterns that were driven by the extreme heat flow and less viscous materials that characterized the early planets. The convection patterns in the magma ocean were likely much more complex and chaotic than those observed in the modern solid mantle, with multiple scales of circulation occurring simultaneously and interacting in ways that are difficult to model or predict. Large-scale convection cells probably dominated the global circulation, transporting hot material from depth to the surface and returning cooler material to the interior. But these large-scale patterns were probably overlain by smaller-scale turbulent flows that created complex mixing and heat transfer processes. The lack of a solid surface meant that there was no rigid plate system to organize and constrain the convective flows, allowing for much more rapid and direct exchange of material between the surface and interior than is possible under modern conditions. The formation of the first stable crustal rocks began to change these dynamics, as the development of a solid surface provided resistance to the underlying convective flows and began to organize them into more systematic patterns. However, the early crust was much thinner and less stable than modern crustal rocks, making it susceptible to frequent disruption and recycling by the vigorous underlying convection. The development of primitive plate tectonic processes probably began during the later stages of the lava world phase, as differential cooling created lateral temperature gradients that drove horizontal flows and the formation of the first discrete crustal blocks. These early tectonic processes were much more rapid and intense than modern plate tectonics, driven by the higher heat flow and less viscous materials that existed during this period. The recycling rate of crustal materials was also much higher, meaning that most of the early crust was probably destroyed and reformed multiple times before stable continental masses could establish permanent footholds on the surface. The interaction between the emerging solid crust and the underlying convective flows also created unique geological processes, including the formation of the first mountain building events as crustal blocks collided and deformed under the influence of the vigorous mantle circulation. Understanding these early geodynamic processes is crucial for reconstructing the conditions under which the first stable landmasses formed, and for understanding how Earth's internal dynamics evolved from the chaotic convection of the magma ocean phase that operates today. The study of early geodynamics also provides insights into the processes that operate on other planets and helps us understand the factors that determine whether a planet will develop